Good morning, good afternoon, good evening. This is Mr. Payne bringing you Unit 6, Lesson 7, Exponential Models Based on Percent Growth. There are many examples of growth in the real world that occur at a constant percent rate. These phenomena give rise to exponential functions. Key word here, exponential functions. Remember, that's what we're all talking about in Unit 6, exponential functions. These functions will be easy to build and understand if you felt comfortable with the latest lesson of percent growth and decay. A population of fruit flies is growing at a constant rate of 6% per hour. The population starts at point 0 with 28 flies. I'm going to highlight some key words here to help us build throughout exercise number 1. So the first word I'm going to highlight in blue is growing at a constant rate of 6%. The population starts, key word here, starts at 0 with 28 flies. So it starts with 28 flies. Some things I want to talk about real quick. If I'm growing, that means that I have to be greater than 100%. So let's remember that. So let's go ahead to A and let's set this up. It says that my time is going to start with 0 hours. So I'm going to just add that in there. And then I have my population of fruit flies is going to be at 28. This just helps me set up my table. Now don't forget, if you don't like following it the way it looks right here, okay, don't hesitate to off to the side to create a table. And you can create your table as X and Y. So you remember that. Really, my X's are my T's in this case, and my Y are my P's. You can set that up with 0 and 28, and then your 1, 2, and 3, and so forth. This looks the same. This here is the same thing as writing it like this. So now I'm going to figure out what I have to multiply by. Well, if I'm increasing or growing at 6% and I have to be larger than 100, I'm going to just take my 100 plus my 6% and I'm going to be at 106%. I want to change that to a decimal because that's how we multiply by, so I'm going to go 1, 2, so it's going to be 1.06. So I will be multiplying each time by 1.06. 28 times 1.06 is going to give me 29.68. Well, since I can't have a decimal for fruit fly population, I'm just going to have 29 fruit flies. After hour 2, I'm going to have 31 fruit flies. And then after hour 3, I'm going to be up to 33 fruit flies. And so forth and so on. Let's go to B. Based on A, find a formula that models the population P as a function of the time in hours T. So one of the things that we have to remember is that our formula for exponential functions is y equals a times b to the x power. Let's just do a quick little refresher that my a is my starting value, what we initially start with, or my y-intercept. And my b is how much I'm increasing by. So what am I increasing by? My multiplier each time. What am I multiplying by? And my x up here is going to be my variable that alters each time. So let's go ahead and write my formula. Y equals, starts with 28 flies, so 28 times my multiplier is going to be 1.06 raised to the x power. Now C says, let's put this to action and use our calculator. You can do this several different ways. It says, what is the value of P of 24? So we can say that my P will equal my A, which is 28, times 1.06 raised to the 24th power. And feel free to go ahead and type that right into your calculator. And when you do, you're going to go ahead and get 113 fruit flies. So D, there's some good vocabulary words in D, and I want you to underline it. It says, what does the calculation you made in C represent about the fly population? State the range of the population function over the domain of 0 to 24. Well, if that is my x values, don't forget, they're asking for my y values. So my y values, which are my p's, will be, if I'm at 0, I look over here, I would be at 28. So my range would be 28 less than or equal to P less than or equal to, and then if I go up here to 24, my Y is 113. So for a domain from 0 to 24, my range would be from 28 to 113. Let's look at exercise number 2 and dive into a little bit of a word problem. If the savings in a bank account can be modeled by the function S of t equals 250 times 1.045, which of the following is true? What I want to do is I want to identify in this formula, because this is the first time you're really getting a good look at this formula, what it means. Don't forget that my 250 is in my A spot. My A starts with is my initial value. Some other words for initial. Starting point. Okay. Now let's take a look at my B. This is written as a decimal. Don't forget, if I want to change this back to a percent, I take my decimal and I move it 2 places. So this is 4.5. If I have 1.045 as a decimal, I bounce it 2 places. My decimal would sit right there. I am 4.5% higher than 100. So I'm 4.5% increase. 4.5% increase. So let's see what what answer is at. Well, I can eliminate 4 and 2 because this says my initial amount is $2.50, and I know that's not the case. So it's either 1 or 3. 1 says that my interest rate is 45%, and 3 says my interest rate is 4.5%. Clearly identifying that 3 is the correct answer. What do they try to get you to do is slip up how you move this decimal place 2 places. Okay, remember, you always want to move the decimal place 2 places. Let's go and work on decreasing now. We should also be able to model exponentially decreasing phenomena based on what we learned in the last lesson about percent decrease. Remember to always model based the percent that remains. So what remains left? So let's read exercise 3 and continue to underline what I highlight so that we can pull those keywords out. As water drains out of the pool, the depth of water decreases at a constant rate of 20% per hour. The depth of the water when draining begins at 12 feet. So we have a lot of information here that we can pull out. When t equals 0 hours, before we start draining at all, my pool is at 12 feet deep. I'm going to now figure out how much is left after each time if I take away 20% of that. And I'm only draining out 20%, so how much of the pool is left? So all I have to do is do 100 minus my 20%, which is going to give me 80%. Remember, change that to a decimal, which is going to give me 0.80. So I'm going to do 12 times 0.8, and I'm going to get 9.6 feet. Times 0.8 again will give me 7.68 feet. And then times 0.8 again, which is going to give me 6.144 feet. B. Based on the A, create an equation that gives the depth D of water in the pool as a function of time in hours it has been draining. So we're going to talk about my D equals my A. My A, let's remember, is my starting value. How deep was the pool when I first began? Well, I hope you can tell me it's 12 feet deep. Times whatever remains each time, which is 80% of the pool. And I'm going to raise that to the t power. Remember, my t is my time, and that's what's going to be changing each time. There is my formula. Now we're going to apply that formula, and feel free to plug this into your calculator. It's safe to cover the pool after it reaches a depth of 1 foot or less. What is the minimum number of whole hours that we should wait to cover the pool? And explain how you found your answer. Well, all I did was I went and I typed that into my calculator and I found out my table. My table looks like this. I have at 10 hours, I have 1.28 feet. At 11 hours, I have 1.03 feet. And at 12 hours, I have 0.82 feet. So we are going to have to wait in order for that pool to be 1 foot or less. So not 1.03 because that's greater than 1.0. We're going to have to wait 12 hours. Let's do some more word problems. Looking at exercise number 4. Which of the following equations would model an exponential quantity? So key word here, exponential. So you know what that formula is going to look like. That begins at a level of 16. So begins at 16. Decreases at a constant rate of 8%. So a couple key things here that I look at right out of the gate. When it says decreases, I know that I have to be less than 100%. So let's take a look at my choices and see if there's anything that's greater than 1%, 100% that we can eliminate. Well, I know that 3 is completely gone. I know that number 2 is completely gone because I'm not adding those in the exponential function. I'm multiplying them. So 2 is gone. Now I have to continue to figure out now what is my multiplier. It says that in my last two answers, both of my a values are 16. Do you agree? I hope you do. Now I have to figure out what my multiplier is. My multiplier is going to be my 100% minus my 8%, which is going to give me 92%. Written as a decimal will give me 0.92. And clearly you will see that it is choice number 1. I hope you're paying close attention to the test-taking strategy that I'm providing here in using elimination. I'm going to do the same here with exercise number 5 to continue to make sure that we're following these steps of highlighting and understanding and breaking down the question before I begin to answer it. Exercise number 5. If $350 is placed in the savings account that earns 3.5% interest applied once a year, then how much would the savings account be worth after 10 years? So a couple things I highlighted that will be really important. How much money am I beginning with? I hope that you can, when you read this, that you realize that we're beginning with $350. So if I were to write that into my equation, I would be $350 times whatever. Now you have to determine, am I increasing or am I decreasing? Well, earns. Earns means that I'm making more money. So I'm going to take my 100%, add my 3.5%, and pay attention how I write this. Because if you notice, I write my decimal a little off. So I'm going to get 103.5%. Let's move that decimal 2 places, 1, 2, and I'm going to get 1.035. So I'm going to fill that in with 1.035. And I'm going to raise it to my 10 years. My years are the things that change. Depending on how many years I save for is how much money I will make. So if you clearly type that into your calculator exactly how we have written, you will understand that my answer is $493.71. If you have any questions, please write them down in the lower right-hand box of your WSQ and bring them to class. We will be doing money practice with this on our worksheets.